My name is James Kelly, and this is my overview of Lab 4, Spring Force and the Energy Principle. Introduction. The purpose of this lab is to create an observed and computational model of the motion of an object attached to a spring. The observed model is created with a video of an object moving back and forth while attached to the spring, put through a software which will track the change of position over time. The computational model is based on a program that iteratively changes velocity over time based on changing spring force and a constant gravitational force, which is then used to update the position. The primary physics principles for this experiment are spring force, force due to gravity, non-constant forces, and the energy principle. The main results of the experiment are that both models are shown to follow the energy principle, and the two estimated periods of oscillation were found to be 1.65 seconds when accounting for only the x position, and 1.5 seconds when accounting for only the y position. The spring force is a force that is sourced from a spring being compressed or extended which pushes or pulls on an object attached to it. A formula for spring force is force of the spring equals negative k times s times L hat, where k is the spring stiffness, s is the change in length between the measured length and the relaxed length, and L hat is just the direction of the spring pointing from the source of the spring to the system that's actually being acted on. A force due to gravity is the force on Earth that pulls an object downwards, which is summarized by the formula force due to gravity equals mass times g. Non-constant forces are forces that change depending on the position, in this case spring force, and net force is the sum of all forces acting on an object. The energy principle is a guiding physics principle that states that the change in energy of a system is equivalent to the work done on the system, characterized by the equation delta E equals W, where delta E is change in energy and W is work. This can also account for work done within the system by calculating potential energy. The conditions of the experiment are as follows. The initial position of the weight was negative 1.107128 times 10 to the negative 1 and negative 6.249919 times 10 to the negative 1 meters. The initial velocity of the weight was 000 meters per second. The mass of the weight was 0.402 kilograms, and based on a calculation done in a separate test, the spring stiffness was found to be 6.83 newtons per meter. The relaxed length of the spring was also found to be 0.123 meters. The system for the position calculations of the weight and the surroundings of the Earth and the spring. However, when the energy calculations are done, the system is changed, being the weight, the spring, and the Earth, because of the need to calculate internal work represented by potential energy. Tracker software results. The video used by the tracker software was provided for analysis and consisted of a weight oscillating on a spring. The video was then put through a tracking software which recorded the change of position over time. A scale was established with a known meter distance. The axes were oriented so the base of the spring was at the origin, and the results for changing the x position and changing y position were organized into different graphs. The exact position values were then used and exported into a CSV file, which would later be used for the computational model. Computational model. The computational model was created using a Python program. The iterations it uses are calculated with a spring force formula at each different position, summing it with the force due to gravity, and using that as the net force. The program then applies the velocity and position update formula to record the movement of the weight. The program also computes the energy changes of the experiment, treating the weight, the spring, and the Earth as one combined system, calculating the potential and kinetic energy. The computed position changes are graphed along with the observed position changes obtained in the program by importing the CSV file with the data from the tracker. Discussion. Observed data versus computational model graph. These graphs were produced by the computational model, comparing the data from both models on its own. The oscillations on each axis are practically identical. On the other hand, the exact distances traveled during each oscillation vary between both models, which calls into question the consistency. Overall, the models display very similar results and allow us to draw some key conclusions. Furthermore, another discussion is the source of error. One source of error is that the time steps used in the computational model were only proportional to those used to measure the position by the tracker. Because the time steps were not the same, it is impossible to say the computational model is a perfect representation of the observed data simply because the calculations are not the same. Conclusion. What does it mean? The first question that may be asked is the validity of the energy principle throughout the model. The energy principle essentially states that the change in energy of the system is equivalent to the work done on the system. When considering the system to be the weight, the spring, and the Earth, the energy principle is fulfilled. This can be seen in the energy graph, where delta E remains constant at 0, meaning no work is being done on the system. Further, based on the data obtained by the tracker, it is possible to obtain two plausible oscillation periods, one on the x-axis and one on the y-axis. On the x-axis, it was estimated to be 1.65 seconds, and on the y-axis, it was estimated to be 1.5 seconds. These estimated periods are very similar, which implies that no matter which axis the oscillation is measured from, it should be similar, if not the same.